Welcome everybody to today's Masterclass webinar on the new features in 8.6. So without further ado, I'd like to hand over to Chris and his team.
Thanks very much, Peter. I'm sitting here in London with there were four of us here in London, four developers. So there's Steve Hendry, Thomas Lee, and Tom Ward. And up in Manchester, we've got Ram Session, and we're all going to be talking about different aspects of the new features in GSA. I'm going to kick off by talking about the 64-bit edition. This is new in 8.5. GSA was only released as a 32-bit edition. Now we have 64-bit and 32-bit. The way we've configured it is, if you're running on a 64-bit operating system, then you can only install the 64-bit version of GSA, and well, obviously 32-bit will only run on a 32-bit operating system. Why is the 64-bit version so great? It's because it is much better at handling large models. There's a heck of a lot more RAM available to GSA when running as a 64-bit application, and well, you can see the sort of difference in scale there, 2 to the 64 versus 2 to the 32 pieces of memory available to the program. So GSA is much more comfortable working with large models when running with the 64-bit edition. Unfortunately, it was quite a struggle pulling together the 64-bit edition. We had to bring in new compilers, new versions of a new edition of OpenGL, the graphics library that we use for the graphics in GSA. And there have been some side effects, which I feel are mostly overcome, but there are some sort of hardware dependencies there. So the problems that we've encountered with the graphics, the positioning of the graphics viewport compared with the graphics window, the graphics selection marks, have mostly been resolved by updating the graphics driver. So that's clearly a sort of hardware/firmware issue. Worth noting, actually, is that even if Windows Device Manager says that you're up to date with your graphics driver firmware, you still can go to the website of the graphics card and find that occasionally there is a newer version, quite a significantly newer version on their website. So it might be worth trying that if you do have problems with viewports or graphics selection. As I say, I mean, actually, so as a proportion of the overall user base, the number of circumstances where that's arisen has been quite small. Likewise, with the licensing issues, we're aware that there are some licensing issues relating to the 64-bit edition. We understand that the people who provide the licensing toolkit are on the case. Meanwhile, we have a workaround where that issue does arise, but once again, it's only a very small number of people who are affected by that. Again, probably hardware related, I suppose. So 64-bit version, generally a good thing. Moving on to steel design, we've introduced a whole bunch of new steel design codes to work with in our steel member checker. So a couple of AISC codes, 2005, 2010, an Australian code, Hong Kong code, and Eurocode. And also, we've extended the range of sections that the steel design checker will work with to include channels and Ts. And those have been implemented for all the supported design codes. And at that point, I'm going to hand over to Steve Hendry. to talk about seismic codes.
Thank you, Chris. Okay, we haven't done a whole lot of work on seismic codes, but we have just done some updates. So we now have the later versions of the ASCII 7 and the Chinese code. There's not much difference between these and the earlier ones, but it's just keeping things up to date. There's actually been more change in the equivalent static analysis option. Previously, that was only available for a very limited number of codes, and they were all US ones. That's now been extended to cover the whole range of seismic codes that we include in GSA. So that just broadens that out considerably. Okay, moving on now to load panel elements. This is a new type of 2D element. The thing about this one is it's non-structural. So you put these elements in, but they don't actually take part in the analysis. They don't have any stiffness associated with them. What they do is they allow us to define loads which are spread over a surface a little bit more easily. And so we have 2D elements which represent areas which are being loaded, and that load then gets transferred onto the surrounding beam elements. So in some ways it's a bit like grid loading, but rather than being defined in terms of a grid, it's defined in terms of these load panel elements. Once you've defined the elements, you then need to decide how the load will be distributed around the edges. And the various options are shown there, from all edges supported to just being supported on a single edge. What you have with all of those options is two things. One, which edges are supported, and then which is the reference edge. And all those are defined as part of the properties for a load panel element. So in the element properties, you just select the element type to be a load panel, and these options are available to you. And this has really sort of been developed for things like applying wind loads, where you want to apply a load which you've got defined over the face of a building. Some of the limitations, well, you will get force equilibrium, but you may not have moment equilibrium. Some of the support conditions simply take all the load and put it on one edge, for instance. And in that case, you won't get complete equilibrium between your applied loads and what's actually being analyzed. So that's something to bear in mind. It's not a big issue, but it is just one of those areas where you can get some lack of equilibrium introduced in your model. You can only use it for a uniform pressure over the elements, so you can't model something which varies from one corner to another. And the other thing is that each of these load panel elements has to be bounded by beam or bar elements, which can be dummy elements, but you do need to have a loop of elements which enclose the panel. You can have more than one element along the edges, so it's possible to have 2 or 3 elements, for instance, along one edge of a load panel, but you do need to have that complete loop. So there's the load panel elements, the basic element. Along with that, we've provided a cladding tool. And the idea of the cladding tool is just to make life easier for you by generating the load panel elements. So it's a convenient way of just taking your structure that you've got and putting the load panel elements around that so that you can apply, for instance, wind loads. Word of warning, what seems like a very simple operation is actually quite a complicated mathematical problem. And so while the tool does its best, it can be caught out if the topology is too complex. So it will work quite well for simple models, but if you get into quite complex topologies, you may find that it just gives up and isn't able to generate things for you. You can control things to a certain extent, but there will be times where it just is too complex for it. So use it, but if it's too complex, you will have problems perhaps. And this has really been implemented to work alongside a wind load generator, which is being developed separately and funded externally from GSA. Okay, so looking at the cladding tool, this is just a very simple example. We're starting off with a frame model. In this case, it's all a very, very regular frame. What we do is we create a list of the exterior elements. So we're just looking at what's on the facade of the building. And we select those. Once we've selected them, we go to the Tools menu, and we use the Create Load Panels on Surface option. This brings up a dialog where we can specify various conditions that we want to apply. The main thing that we want to look at here is that the element list defining the surface, we can either put the list in explicitly there, or in this case I'm using the one I created called exterior. When you click OK, that goes off and generates the cladding elements, and so you can see here the 2D load panels that it's created for us around the facade of the building. And then finally there's our clad model. So we've got our structure there, and we've got our load panels around the outside ready for applying wind load or whatever else we want to apply. So that's the cladding tool. And then we come to the element thickness modifiers. We've had element thickness modifiers in GSA for some time, but those have changed a little bit in 8.6. Part of the difficulty was that once you started applying thickness modifiers, it wasn't very clear what would happen to the mass or the weight of your 2D element. In order to clarify that, we've introduced a new thickness modifier. So alongside the bending and in-plane thickness, we've now got a thickness for the mass and weight calculations. So something like the gravity loading will now be based on that mass weight thickness, and so it's clearer exactly what you're getting. And we've also tried to clarify what thickness gets used for the various 2D element results. So things like the in-plane forces, NX, NY, and XY, they're based on the in-plane thickness. So the forces that you're getting are consistent with the stiffness that you're using to calculate the results. Likewise, the moments and the through thickness shears are based on the bending thickness, which is what's used for the stiffness of those elements, or that part of the element. The thing which is different in this version is that the stresses are all based on the actual thickness. So that means that the stresses that you see will be based on a different thickness from, for instance, the bending moments. And so there isn't that direct relationship between them that there was before. But it seemed better to calculate the stresses based on the actual thickness. So that's something which means that any stress results you get will be different, although the other ones, the moments, the forces, should be the same as before. So that's just a sort of word of warning there. And at this point, I'll hand over to Thomas.
Hello, this is Thomas Lee. I'm going to introduce you the wall element in this version of GSA 8.6. Why we have implemented wall element in GSA. So I guess if you have used 2D element in any FE software, you want to model a wall or model a slab. If you use normal shell elements, 2D elements, you have to mesh the 2D element to a smaller element size. For example, you got a wall element 6 meters by 6 meters. Probably you have to use a number of small shell elements. So the meshing make the structure complicated and also make the general stiffness matrix larger. So ideally, as an engineer, I'm an engineer as well. So I like to use one element to model a wall or model a slab. But for normal shell elements, this is not possible because the formulation of the 2D element, we can't use one element for a single wall, single slab. So this is why we have implemented wall element in GSA. So what is wall element in GSA? Basically, it is a large 2D element. You can say like that, or you can say it's a super element. So this large element will give you accurate results if you just use one element to model a single wall, for example, 6 meter by 6 meter wall. So internally, we still mesh the wall element. So in current version of GSA, we mesh a wall element by 4 by 4 quad 8 shell elements. So but you don't need to bother, because when you define a wall element, it's just a 4 node 2D elements. So the results from wall element at the moment are only available for the 4 edges. You know that's 2D element, they have 4 edges. The edges will have moments, 3 forces. And we will present these forces on the edge by equivalent beams, or you call it a wall stake. That's a way we present wall element results. But in the future, of course, we want to know the internal forces within the elements, but that's not available in this version of GSA. Another advantage of using wall element may be the rotational stiffness about the normal direction of the wall element. We know for normal 2D element, shell element, they normally don't have rotational stiffness about the normal direction of the wall element, about the 2D elements. The normal, this stiffness normally, sometimes we also call drilling stiffness or drilling degree or freedom, something like that. So because wall element is messed up internally, so that gives us opportunity to generate this rotational stiffness pretty precisely, accurately. So using wall element, I guess this in the future, maybe we are going to improve wall element as well. For the advantage of using wall element, I think probably 2 advantages. One is simplify the modeling of the structure, and another one I mentioned just now, the general stiffness matrix size will be reduced, so that may require less memory for analyzing the whole model. You can see here is a one wall element. It's messed up by 4 by 4 shell elements, quad 8 shell elements. So the numbering of the nodes and the edges are the same as normal 2D element, the same as quad 4, exactly. So they are internal nodes and external nodes, because we mesh it. You will see they are internal nodes and external nodes. The internal nodes will be condensed off in the global analysis, and only the external nodes will be included in global analysis. So that can make the global stiffness matrix smaller. As said, we present wall element results by equivalent beam or wall stake. So here shows the equivalent beam. One called primary, another one called secondary. I think you will see clearly on this diagram. So the primary one is from direction is from node 1 to node 2, and the secondary is from node 2 to node 3. So if you ask for wall element primary results, forces and moment for primary direction, you will get the edge force and moment for edge 4 and edge 2. Similarly, if you ask for secondary direction, you will get the forces and the moments and H1 and H3. As said, a wall element got a drilling stiffness. So here is a way how the drilling stiffness has been generated. So basically, we add 4 dummy nodes at the center of 4 corner elements. Then we link this dummy node to the corner nodes by a beam element. So the actual generation is shown out here, if you like to know. So this is one of the quad 8 element at the top right corner of this wall element. So we got dummy nodes. So we have constrained this dummy nodes vertical displacement to be the same as the horizontal edge, the middle nodes or horizontal edge vertical displacement. So these two nodes got the same vertical displacement, and these two nodes will have the same horizontal displacement. Then we add a beam from this dummy node to the corner node. So the beam section size is very large. It's a very large section size. It's not fully rigid, but very large. The beam is connected to the dummy node by pin, the pin to the dummy node, and fixed to the corner node. So you can imagine if the corner node going to rotate, if you connect the beam to the corner node, the beam has a rotation, the corner node try to rotate. If corner node try to rotate, it will drag this node moving. So that's equivalent to rotate this rectangular area, something like that. So in this case, if you connect a beam element to the wall element, the beam section size similar to this rectangular area, the wall element drilling stiffness will be pretty accurate. But if we connect a larger section, the drilling stiffness may be underestimated. But we are going to improve this in the future. So there are some limitations for wall element in current GSA. So basically, these are the main limitations I listed on here. The first one is the wall element must be rectangular. So the next one, so it can only be used by linear static and model dynamic analysis. If you do other analysis, buckling analysis, so you can't use wall element in this version of GSA, but in the future, it should be possible. One advantage we use wall element, we get the results very intuitively. You know, you got wall element as a result, it's a force moments. So ideally, people may want to get force moment for a group of wall elements. For example, you model a core using a core is rectangular core. You are using four wall elements. So ideally, you may like to know the forces and the moments for the whole core. That means a group of 4 wall elements, but this is not available at the moment. A cut section force can be used for a wall element at the moment. So you may want to connect other element to the wall element. So at the moment, you can only connect it to the 4 corners of the wall element. Because wall element is large, sometimes I guess you may want to connect a beam element to the middle or the edge of the wall element. But at the moment, that's not possible. It's possible you can use tight interface to connect to the middle or edge of the wall element, but that will generate some errors. The results I said only available for the 4 edges that will be given by equivalent beams or wall sticks. So in the future, we are going to output results like stresses, moment inside the wall element, similar to 2D element. You got shell element, you know you can get the forces, stresses inside the 2D element. But in the future, that will be available for wall element as well. So drilling stiffness in this version is only accurate if your beam section connected to the wall element is 1/8 of the wall element size. If you connect a larger beam element to the wall, the drilling stiffness may be underestimated. Yeah, I think that's all for the wall elements. I will pass to Thomas Ward.
Thank you, Thomas. Thank you, Thomas. That was really nice. Okay, I have just a couple of things I would like to touch on briefly. This one actually follows on quite neatly from what Thomas was talking about in terms of walls. We've also added the drilling degree of freedom to our linear 2D elements. So that's the Quad4 and the Tri3. Excuse me. So for example, if you were to think of a shell element. At the moment, we have what we are now calling the bilinear formulation, which is the 5 degrees of freedom per node. And it turns out that's actually sort of what's for a finite element formulation. That's all that's really necessary. But clearly, there are advantages with having all 6 degrees of freedom activated. And so we follow some work by Alman Cook that produced a formulation that we also call it just the drilling formulation that now activates all 6 degrees of freedom. In fact, Cook calls it, sometimes it's referenced as, actually, let's just think of a plain stress problem. It's slightly just simpler if we've just got X and Y translations per node in a quad 4, so that's just 8 degrees of freedom. If you were to do that with Alman Cook, you would also have the X and Y translations at each node, and now also the rotation at that node as well. So that's 3 degrees of freedom per node, so that's 12 degrees of freedom, not 8. And if you were to consider a quad 8 element, in the same format, you'd still only have the X and Y translations, but with 8 elements, that's 16 degrees of freedom. So in some ways, we can think that the Alman Cook sort of 12 degrees of freedom is halfway between the original bilinear quad 4 and a sort of a more fully complete quad 8. In fact, Cook references it sometimes as a quad 6, just sort of colloquially as a sort of a way of sort of expressing that. We are, in fact, as I said, this is in plane, so we're just talking about the performance of the elements within the plane. In fact, it's not dissimilar to the sort of work, if some of you remember from previous version, I think it was 8.5, where we introduced the MITC formulation that did, okay, it was through a different mechanism, but sort of solved the same sort of problems in terms of its flexibility, etc., in the out of plane. So this is doing a similar sort of thing in the in-plane. So briefly, so in terms of practically, well, that's it really. It gives you access to that degree of freedom. You can get rotations at that degree of freedom. It avoids the use of automatic constraints. I won't go into that bit. For those of you who use them, it just means that now there's no drilling degree of freedom to suppress, to constrain, because it's a genuine part of the formulation. So that's quite neat. And numerically, just, well, as going back to previously, because we're sort of a quad 6, we're halfway between. In fact, it turns out that the 4 degrees of freedom that we've added, these drilling ones, the shape functions associated with them are the one in that little diagram on the top right, which are actually parabolic. So those are the sort of, in fact, turns out to be the exact bending strain states that are useful to alleviate problems such as shear locking that are present in the sort of the bilinear formulation. And in fact, that's the same idea with the MITC thing as well in the outer plane. So yeah, the two sort of are quite compatible there. There is a trade-off. Caution, because they're not reliable for connecting beam elements directly through a single point connection. So what I mean is, if you have a beam, connect it to a slab just through a single node, or in fact apply a moment just to a single node. In some ways, this is quite typical of a lot of points of finite element bursts. We are, especially in this example, because of the size of the element, what does a rotation mean? Well, we're applying a rotation with respect to some kind of area. Now, in maths, you can have a rotation at a point, but we have to define a rotation about an area. That, of course, is the area of the element. When you have small elements, the stiffness, the rotational stiffness can be quite small. You're applying it over a very small area, so you can get very sort of flexible local deformations that are unnatural in the sort of the local area. So in fact, as an example, and Chris actually will touch on this again later as a way of doing this automatically, well, a tool to help you do this. In this sort of situations, you can see it is recommended to sort of use something like a rigid constraint to distribute that connection over a finite area, not at a point essentially, which just makes that connection much better. So that's what I'll say there. But yeah, that's useful. And the other thing I'm just going to touch on is we've added the calculation of the torsion constant for any arbitrary perimeter section. So this works very much like any other sort of section property you'd find in the section wizard for perimeter sections. It works almost like any other. We have added actually a checkbox, calculate torsion constant, which you tick. As explicitly. That's only because this is running a slightly more in-depth calculation. It does take a bit more time, I say a few seconds, but if you've got a lot of sections, that could add up. So if you're not interested, you can leave that unticked, and it just saves you a bit of time. So whereas things like calculating the area is trivial, so obviously there's no reason to ask for that. I mean, in terms of actually using it, that's really all it is to say, tick the box and go, really. But it's useful to know what's going on behind the scenes. So I just do one slide, just to mention in terms of what it's actually doing, just to get some kind of context as to the calculation. One thing I'll just say here, it is restricted to thick wall sections only. I think the perimeter section dialog in general is sort of designed for sort of thick wall sections, and I think a lot of you will recognise that a thin wall section would be better suited by sort of specific thin wall theory, which is something we might look at in the future, but for now this is very much focused. In fact, it will give you a warning if it considers your section to be too thin. Just go on there, but I won't. But if it considers it to be, it will give you a warning, say, hey, come on, this is looking a bit thin. So probably slightly better English than that. But, okay. Just behind the scenes, very quickly in terms of what it's doing, it is solving a domain problem, a field problem in 2D for this. Uses the boundary element method. Typically, we would use a finite element method, but it just so happens that this problem really lends itself to sort of a boundary element type solution. You can see in this example, for example, we just have to mesh the boundary, which is what you can see all the dots on the boundary, which is quite nice because we sort of reduce the problem size by 1. Instead of a 2D problem, it's now just a one-dimensional problem, which makes it quite quick. And we're solving for this thing called phi, this stress function. It's a sort of scalar potential excuse me, function, which is easier. I mean, we could solve directly in terms of strain states and displacements, but it turns out the boundary conditions get quite ugly for this. So it actually the general approach tends to be to do a change of variable to this scalar potential, and it's the stress function. It's a bit like the stream function in fluids, same kind of idea. And we take the derivatives of those, and the derivatives of those happen to be the stress. And from this, you can then integrate on the area, etc. And then that itself gives you the torque for this twisting problem, and from that, the torsion constant. So that just gives you a bit of background. But it's, I mean, that's all hidden. That's a MATLAB shot. That's not even in GSA. But it just kind of gives you some context to what's going on. I think that's all that worth mentioning at this stage on that. We're gonna. I'll introduce Ramseshan. He's there. He's not with us. He's in Manchester. So I think do we need to enable a microphone? He's done it. I can hear you. So yeah, Ramseshan,
yes.
Your microphone over to you.
Very good. Thanks, Tom. Can you also pass me control, mouse, and keyboard, please?
I knew that's something we had to do, Chris. I'll leave that to you.
Do you not have control? Have a go.
Yeah, I think I do, except, yeah, okay, very good. Thank you, Tom. Yeah. Right, so I'll quickly run through the improvements to the solvers. Most of the improvements are, in fact, all of the improvements are in the area of GSS solver, which is the solve for linear analysis. So we've got a new sparse direct solver that makes use of multiple cores on your machine. So increasingly we have desktops and laptops that have more than one cores, and we would it's desirable to be able to take advantage of the extra computing power that's being made available. So the new solver uses multiple cores available on your machine for factorizing the stiffness matrix, and it's many times faster compared to the existing solvers in GSA 8.5. Although I must add that the speed up that you might experience in the overall solution might be only marginal, because the other bits are not parallelized. So within the solution phase, we've got the assembly of the stiffness matrix, factorization of the stiffness matrix, solving for load cases, and then calculating forces and moments. And we only parallelize the factorization of the stiffness matrix, but we are looking at parallelizing the other bits as we go. So in future releases, you can expect a more parallel solver from GSA. The other improvements in this area are an improved procedure for assembling the stiffness matrix. So it's now faster and takes up less storage to when you're assembling the structure stiffness. Okay, I'll wait for the screen to catch up. Takes time. Right. The other addition is the condition number estimator. So the condition number is a quantity that tells you how well conditioned or ill conditioned your model is. Mathematically speaking, the condition number indicates the maximum possible error in displacements when you're solving a linear system. So when you're doing a static analysis, for example. So a high condition number can imply that your results can contain errors. So you ideally want a model with a low condition number. If you have a structural model that has a condition number that's greater than 10 power 16, then your model is almost singular, i.e. it's very ill-conditioned. And the results can have a high degree of error. So these errors occur because of the rounding analysis that's inherent to calculations within any finite element software. So the condition number now gives you a firm handle on how much error can be introduced by these by the rounding of floating point numbers. This is a new feature we've added in 8.6, so you might not have seen these warnings in 8.5. So some users have reported to us that their models that were running fine in 8.5 have suddenly started giving errors in 8.6, and that's just because we didn't have this check in 8.5. But in 8.6, if your model is ill-conditioned, then it will tell you that it is. We are producing some guidance as to how to interpret the condition number and what the sort of the underlying mathematical formulation is. It also touches a bit on what leads to an ill-conditioned model and how we can create models which are reasonably well-conditioned. Okay, wait for the next slide to come up. So the other improvement is, oops, sorry. The other improvement is being able to save, auto-save a model after having done batch analysis. So if you set off batch analysis and you want to go away for the evening, GSA will now offer to well, there's an option to automatically save the model once the analysis is done, and this is available from the preferences in the tools. Moving on to enhancements to the COM interface. For those of you who use a COM interface, you might have noticed the GW command works with single records of data. So if you want to retrieve node information, you have to iterate through all the nodes one by one, and that takes up a bit of time. It also means that you make lots of COM calls, one per node, for example. So the GW command getAll option retrieves all nodal all information for a particular module in a single function call, and you can then sort of obtain this information as a piece of string that you can pass. So that would mean reduced number of calls to the COM interface, and that should speed up the extraction of model data. Analogous to that is the outputir function call, which is to do with extracting results and output information in form of an array. So given an element or node, you can now retrieve all results pertaining to that entity in a single function call. What that means is lesser number of calls to COM interface, but also it means lesser number of loops in your code, which will all result in an overall speed up. Then there are new view functions to manipulate saved views, so you can create new saved views from existing views. You can delete them, edit the entities that they refer to, edit the cases, and so on. You can explode a list given its description. So if you have a list a piece of string that stands for list, for example, P1 to P10, you can then call a COM function, just pass it as a string, and then it will return. GSA will return you all the elements that are part of that list. And finally, node connected end returns all entities that are connected to a node, and that comes handy when you're trying to extract element forces on nodes, for example. And I think that's it from me at the moment, I think. So yeah, back to you, Chris.
Session. Oh, thanks very much for the session. So I'm going to whiz through a few of the other features that come along with GSA 8.6, starting with 2D element center-only results. As we all know, we need a lot of accuracy in our finite element meshes to accurately represent the behavior of the structure, but we don't always need the full detail of the results when post-processing. So if you consider that you're only ever going to need results at the center of elements, having established that the behavior of the structure is as expected or as required, then in the advanced solver settings you can choose to switch off the nodal results, the storage of the nodal results, and just have the 2D element forces and stresses at center only. And that will considerably reduce the amount of data that's stored in your results from, for Quad 8, from storing results at 9 positions to storing at just 1 position. So that will sort of reduce the amount of memory used by your model, as well as the amount of the file size. But whether or not you choose to store the results at centers only, you can choose to display results at centers only, whether as contoured display or diagrams. And you can imagine that that will significantly speed up the post-processing. So, for example, if you are getting reinforcement contour plots in an RC slab design, then you're going to speed up the production of that 9 times. And you get the sort of display that you see there, patchwork quilt look. And note that if you're into using user modules, there's a new center-only 2D flag. So again, you can store center-only values in user modules. Okay, moving on to a few miscellaneous items. In no particular order. Edge loads on 2D elements. Well, in the past, you could only apply edge loads as a pressure. There's a new option now to apply edge loads as a force per length, which might be more convenient at times. Constraint stage lists. If you're using analysis stages in your model and you want to switch on and off constraints depending on the stage, then in the past you had to have a different record for each stage, even if you wanted the same constraint applied to several stages. Now you can just have the one record and refer to a list of stages. Load names. You can choose to assign names to your loading if you wish. I've chosen thread here, but you might think of something more appropriate. And if you've got a name assigned to a load, then that appears in the output table for those loads. Note that those names are only visible in the input tables if you've got that preference set on the input tab, show names in loads tables. Spreadsheet interaction. There's an option amongst the output settings to fully populate fields, and all that means is that instead of the output being displayed as if it were in paragraphs per element, you just get the same value being repeated all the way down the list. And there's also a little tweak to where the units are displayed, which seems quite trivial, but actually when used to export data to a spreadsheet, suddenly it becomes quite useful that you've got all that data populated in the fields, and you can use the filter and pivot table features more conveniently. Some other output options, there's a new table of beam section extended properties, which reports those same properties that are currently listed in the more properties from the last page of the analysis wizard. So presumably, previously they were only displayed in a dialog box. Now they're listed in a table in case you want to copy them into a spreadsheet or whatever. The grid planes output now includes grid plane areas. For those various detailed output section options, mass details, dynamic details, etc. They now recognize the case list, so you can specify for which cases you want to examine those outputs. And note that the case list can be expressed in terms of tasks. So T2 refers to all analysis cases that were analyzed in task 2, for example. Graphic view selection options. If you right-click on an element and go to select property, then all the elements that reference the same property are automatically selected. Similarly for groups and materials. There's a split plane option. What I've done here is I'm looking at the elevation of a structure, my favorite structure, and I've specified an inclined grid plane, and I've chosen to split at that grid plane. And then what I subsequently did was delete all the elements on one side of that grid plane so as to illustrate how that worked. And it seems to have chopped the elements along the grid plane in half, or at the intersection of the plane, quite neatly. And the options are, that option is available in the split 1D elements dialog, and you can either choose to split at a grid plane or at a plane defined by 3 selected nodes. Then there are some Sculpt options to align elements, so you can align 1D elements such that they all point in generally the same direction, aligned with grid axis directions. Align 2D element edges such that they all generally point in the same direction. The x-axis of the 2D elements generally align. Or align 2D element z-axis so that they all point generally upwards. And then moving on to the Sculpt option to connect a column to a slab. This is something that Tom referred to a bit earlier. So the idea is that we want to connect a column to a slab and to carry the rotational stiffness of the column through from the column to the slab itself, and that's achieved by assigning rigid constraints to the nodes on the elements attached to the column. And you can choose either to always assign all the rigid constraints to all the nodes on all the elements attached to the column, or you can limit it based on the dimensions of the column or based on the radius, a specified radius, and only 2D elements that are within, have their center within those dimensions are then included. And finally, just to mention that GSA now works with Revit Structure 2012 in the GSA Revit link. And at that point, I hand back to Peter.
Wonderful. Thank you very much, Chris.